Recording in progress.
Hello, good evening, Josh.
Hello.
Euler's totient or phi function. We'll be doing some applications of the phi function in problem solving. So our third problem for the applications is make a list of the positive integers less than 18 that are relatively prime or co-prime to 18, and hence show that the totient function of 18 is equal to 6.
So we do the simplest way is to literally write all of the positive integers less than 18. So I will list them down first. Oh, I will just use the dark blue. So it will contrast to the black. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. Okay.
Yes.
So 18, I will put in red the prime factorization.
Tap mo, baka you might not have enough space.
Okay. The prime factorization of 18 is 2 times 9 or 2 times 3 squared.
Yes.
So the numbers that are listed here that have any factor of 2 or any factor of 3 cannot be co-prime to 18, so we will cancel them out.
Meaning
They have a common factor.
2 and 3 could be either 2 or 3 or both could be
Their
common factor.
So of course 18 no, and then we just cross out the multiples of 2,
2, yes.
and then of 3,
The
3,
remaining
6,
multiples of
9, 12, and then 15,
15.
18. So we are left with the
how many?
1,
1,
2,
3,
3,
4,
4,
5,
5,
6. Yes.
Yeah, so apparently
There are-
we have already proved that
There
the
are
totient of 18, or the numbers, the positive integers less than 18 that are relatively prime to 18, there are 6 of them.
yes. So there are 6. Can I add something? Meaning you call this 6. There are 6 totatives of 18, which are 1, 5, 7, 11, 13, and 17. What do we mean by totatives?
Totatives are just like what the problem says. Those are the positive integers, all of them, less than 18, that are relatively prime to 18.
Okay,
And
so
it is assumed that
totatives.
one is always one is relatively prime to every positive integer.
Yes. Okay, so alright. So totatives are positive integers less than 18 that are, excuse me, can I have some space, that are co-prime or relatively prime to 18, meaning they don't have any common factor with 18, since the prime factors of 18 are 2 and 3, so 2 and 3 are not their common factors. Okay,
Yes.
so here
So now, so we have a sub question for B.
yeah, you can,
You can put this B.
yes, for B, for
Okay,
each
so
of
for B,
these positive integers x, work out x to the power 6 modulo 18.
and just like everything, we once again do it the hard way. We will try each of them. There are only 6 anyway, so we just have to try 6 powers of 6.
Can you go to the next page? I think you will apply the what theorem?
We will apply the Euler-Fermat theorem.
Fermat's. Yeah.
Yes.
Put
Actually,
apostrophe s.
there is
Yeah.
no apostrophe s. Anyway.
Theorem, yes. which states what?
If x is any positive integer co-prime to y, then x to the
Raised to the
phi
power
function of y is
yes,
equivalent to 1 modulo y.
yes. So
So
what do you mean by that? So
so
if the phi of 18 is equal to 6, then
we can just express 6 x
so
to the
right
6
first if
mod
phi
ah,
here on top. Let me
if
help you. Yes. So if
phi,
phi of 18 is equal to 6, then what?
then we can express
Express it in the
6x
using the Euler's
mod
Fermat.
6x mod 18 as 6 to the phi of 18 mod 18. And then because we can identify which is the y, that's 18. So then this is equivalent to 1. Okay, so I will just put it here on the below because it won't be mathematically correct. 6 to x to the 6th, or the totative
Oh,
of
you can
18
yeah, okay.
is
Is equal
equivalent
to
to
x
1.
to the 6 first.
Ah,
So those who are trying to learn will associate that x phi of 18 is equal to x to the 6, yes.
which is equivalent to 1 because of the Euler-Fermat
1
theorem.
modulo 18. Yes, so yes. So what do you mean? So let's use the totatives of 18, right?
Yes.
So for
So
example,
let's just do it na. Let's just do it. Okay, so 1 the 6th and then over 18. So we'll just find the remainder manually. Of course.
so can you write first here on top the totatives of 18?
Oh yes, totatives of 18. Tot 18. 1. What are the totatives again?
1,
1,
5,
5, 7, 11,
7,
13,
11, 13, 17.
14. Okay, 1, 5, 7, 11, 13, 17. Okay. So
We start with
we start
1.
with 1, 1 to the 6 over 18. Of course, 1 to the 6 is just 1. So 1 over 18 immediately, that is 0, 1. I will just use a different color for the remainders. 1. And then for the next one, which is 5 to the 6th over 18 is equal to 15,625 over 18. So if you just use a calculator or you want to do it yourself, it will just become 868 remainder 1.
Okay, so let's translate this to your Euler's Fermat theorem formula.
So
The 1, what happens to the 1? 1 to the 6 is
1 to the 6 is
equivalent to
1, which is just equivalent to 1
1
mod
modulo.
18.
Yes, that's how. This is the interpretation of that.
Actually, I don't think it's good to use that. This equals 1, which is then equivalent to 1 modulo 18.
Okay.
Ah,
So
okay.
and this one,
This
5
is
to the
5 to the
6.
6. That is equal to 15,625. Is then equivalent to also 1 modulo 18.
Yes, 15,625 equivalent to 1 modulo 18, meaning if you divide 15,625 by
By
18, you will get a remainder of 1.
Yes.
Okay, so let's turn the page.
Next page. So
Seven.
then now I'll just put the totatives again so we won't forget.
Yes, 1, 5, 7, 11, 13, 17.
Okay, so now we are
Two
at
commas,
7.
so yes.
7 to the 6th over 18. So that is 7 to the 6th. That is 117
117,649.
49 over
18.
18, which is
6,536.
6,536. Remainder, yes, 1.
Remainder, still remainder 1.
So again, in modular arithmetic, modular arithmetic.
Yes,
Yes,
the
okay.
Euler-Fermat theorem.
76. It's not really Euler-Fermat theorem. It's just modular arithmetic. 649. Okay, is equivalent to just 1. Mod 18. Okay, so next one we are at, okay, so I'll just put a stamp mark. 1, 2, 3. We are at 11.
Yes.
11, 6 over 18. So now the numbers are getting larger. 1,
1, 7, 7,
okay,
1,
wait. 1,
7,
7,
7,
7,
1,
1,
5, 6, 1.
561
Over,
over
yes.
18, which is
98,420. Remainder, still 1.
1.
So
So
this is meaning if you divide that number by 18, you get
still
a
get a
remainder
remainder of 1.
1.
And then 13, 13, 13, 13.
13 to the 6. That's 4.
Okay, they are becoming too large.
Yes.
4.
4826.
I can type well.
4826.
Okay, 2, 6.
809.
Yes. Okay, so
Divided by 18
divided by 18.
is 268,156.
268
156.
156.
Remainder
Click R 1.
yes.
Yeah, so 13 to the 6th, 4, 8 to 6, 8 to 9.
That's still
And then finally
17 to the 6. This is 224 137 569. Equals 1,340,976.
yes.
So since
Since 1 to the 6 is equivalent to 5 to the 6 which is also equivalent to 7 to the 6, which is also equivalent to 11 to the 6, which is equivalent to 13 to the 6, and equivalent to 17 to the 6
That is
is
in
equivalent to
modulo
1.
modulo
18.
18. Yes. Other forms of 1 modulo 18 could be.
B.
Oh no, you write it that
No,
way.
it's not.
It's okay.
You must put the modulo after. It's equivalent to 7 cubed or 13 cubed. Those are other forms.
Of oh, 1 modulo 18.
It's the same.
No, put it clearly for those who are learning. Yes. Okay. So
Yes.
going to next page. So how did you get that one? 7, let's say 7 cube.
Yeah,
Why is it 1 modulo 18?
it happens that 7 cubed over 18, which is 343 over 18, is exactly equal to 19 remainder 1. So
Yes.
yeah, so we again end up with the remainder 1. This is rather by chance. And then 13
13.
cubed over 18 equals 2197 over 18
That's
equals
22.
remainder 1.
I could. Oh, wait, I'll get the calculator. Could be. What's the number?
2197 over 18.
Divided by 18. 122.
Oh, 122.
Yes.
Okay.
Okay, so wait. So let's try the next number, number 4.
Number 4. Number 4. Okay, so I'll just put it here. Number 4.
I think we already made the problem.
Uh-huh. 4.
Yeah. Solve the totient function of 7 million over the totient function of 1 million.
Totient.
Phi.
Wait. I'll just extract the phi.
Just write it. Phi.
I can't write the phi, it's not on the keyboard. Okay. Solve phi 7
Million over phi 1 million.
Oops. With the cropped. Over phi 1 million.
Yes.
Crop. Okay.
It's I think
Yes.
fairly simple. It looks
It
intimidating, but then it's actually what fairly simple, right?
It's actually even more intimidating because we can extend this to 7 Google over the phi of 1 Google.
Yes.
It will still be easy. So the first solution, which is based on if you have any knowledge on the totient function. So
Yes,
the totient function is
You
multiplicative.
you can check our first video on the totient function, the lecture on totient function. Everything's explained there.
So, oh, I'm still using the black.
Let's equate
So
it here.
the
Let's equate
totient-
it here. So yes,
Okay.
can save some
So this
space.
is, it's also multiplicative. So 7 million is of course 7 times 1 million. So
Yeah.
this is equivalent to the totient
Yeah.
of 7
It's
times
the
the totient
multiplicative
of 1
property of
million.
the.
Yes. It also is multiplicative because of its formula rin. It's also multiplicative because of its formula. Actually, most of its formulas are multiplicative. Okay, so apparently we have a common. I will just use red. It looks doesn't fit well. Okay,
So
so
you end up with.
we just end up with phi of 7. So like I was saying earlier, we could have changed this to 7 million Google, and then the other one's 1 million Google. And it
Yes.
won't change because the end result is only phi of 7.
And 7 is
Is prime. So 7 happens to be prime, so we have an even simpler way of
solving.
reducing it. So it's simply the prime minus 1 or 6.
That's our final answer.
Or we can just
show
using
them
just
your
using
algebraic
the
solution.
yes,
So
using
solution number 2.
just using if someone just gives you the
So
formula
put solution
of
number
the
2.
to
Solution number 2.
so let 1 million.
So this is the other solution of Joshua. It's algebraic,
This
but it
is
also works.
this is the of course it must work because this is just the form. This is just part of the formula of the phi function, but I just omitted multiplying the 1 million itself, or
Okay.
otherwise it would have been the phi of 1 million. So phi of 1 million. So like I said earlier, I just omitted the 1 million part. So of course this should be xy. Okay, so now this looks too much like y. Okay, so now we give justice to the Greek language, xy,
So
and then therefore the phi of 7 million. So I'm using this this block because
Use a different color.
because 7 million is 7 million sa prime factorization. I forgot to put the
Yes.
prime factorizations. So the prime factorization of 1 million, because it has 6 zeros, so that's 10 to the 6, 2 times 5 to the 6. Looks like this was cancelled too. Just
So by distributive property of
exponents.
the exponents.
So
Yes.
to the 6 times 5
Very
to the 6.
good.
And then so of course 7m I'll just abbreviate. So 7 million is 7 times 10 to the 6, or 2 to the 6 times 5 to the 6 times 7. So we just multiplied 7 anyway. So it's clear from the start, but that will reflect on the phi function. So of course that's 7 times 1 million, so that's just 7x, and then this is y, which is this block, and then since there's an extra 7 in the prime factorization, I will add 1 minus 1 over 7. Yes. So the phi function, however, of wait, I already listed it down. The phi function of 1 million is xy. So now I will simplify this. This is 7xy times 6 7s equals 6xy, because it is cancelled. Okay, so 6xy. So therefore, the phi function of 7 million over the phi function of 1 million is simply 6xy over xy, and then the xy this time cancels.
And
So
you're left
we're
with...
just left with 6 again.
Yeah, so, but wait, let me just clarify this one. So, they might be wondering, where did you get 1 minus 1 over 7? I think this is the one, right? If you multiply,
Yes, you can put the formula above.
yeah, so this is 1 minus 1 over 7.
Oh, it's not equal.
Ano na equal?
No,
What is it?
it's part of the equation. So the equation, one equation for, especially for composite, no, it doesn't. It also works for prime numbers. It just so happens that there is no other prime factor. So it's just, so in the end, the prime is just 7 times 1 minus 1 over 7. So sort of like that. But the general formula for any phi function, this is just one of the formulae. Any phi of x is equal to whatever x is times 1 minus 1 over what one of its primes. I'll just put let's say let x be any composite number. This is general form.
Yes.
So it's, of course, it's just many primes raised to their respective powers and then all multiplied. So this is the 1 minus the first prime, and then times 1 minus the second prime. Of course, the order does not matter, and then it just keeps on going, and then 1 minus the last prime.
But here you have
So
only...
here we have, in the first example, we have 2 primes. Those are 2 and 5. So I already listed down. Here there's 2, and then here there's 5. I'll just put the little laser
So why,
pointer.
no, why did you use here 1 minus 1 over 7? Because of the 7?
Yes. So because of the 7, because of the 7, we now have a third prime, which is here in the Pn. So the 7 is now Pn. So it gets substituted as 1 over 7. So I will put the one here. Phi of 7 million is equal to 7 million itself times 1 minus 1 over the first prime factor times 1 minus 1 over the second factor times, of course, 1 minus 1 over the last form factor, which is 7. Okay, so we can substitute again if it wasn't clear. 7x, because 1 million is the x. And then this one, this block, that is y. We declared that earlier. Y, and then times 1 minus 1 over 7. So that's how we got this one.
Okay, nice.
Okay, so 6. That's our final answer.
Yes, thanks for solving these two beautiful problems regarding the Euler's totient function or phi function. Thanks for...
Thanks for watching.
Yes.
I hope you learned a lot. Okay.
Yes. Bye.
Bye.